Hi everyone, my name is Sarah Fuller, and in today's podcast, I'm going to be talking about open channel flow. The lab demonstrating open channel flow was completed in the Talbot Lab at the University of Illinois. The objectives for the open channel flow lab are determine the free surface profiles for steady, slowly varying flow in an open rectangular channel, and to compare these profiles with those predicted by the theory or for free surface profiles for the given bed slope and Manning's roughness coefficient for the channel. So first, the procedure. First, the bed slope was measured by closing the downstream gate and filling the channel as full as possible without flooding the system. The depth was measured at 6 evenly spaced points, and the slope was measured using the data earned. Step 2. A uniform flow was established by removing the downstream gate and adjusting the upstream gate until a negligible variation in the depth was obtained. The depth at the 6 points were measured again and averaged to obtain the depth. Step 3. The flow rate was measured using the weighing tank. The flow rate was remained constant. Step 4. The upstream gate was raised fully, assuming S2 profile. The depth at 6 locations were measured and averaged. Step 5. S1 profile was established by raising the downstream gate slowly, enabling a hydraulic jump. The height of the downstream gate was chosen so that the hydraulic jump occurred far upstream as possible. The depths at 6 points were measured and recorded on the data sheet. In the first equation, Manning's roughness coefficient, N, is used to determine the flow rate, Q, in an open channel for normal flow, where RH is the hydraulic radius of the channel, A is the cross-sectional area of the flow, P is the wetted perimeter, and C is the Chezy coefficient given by the second equation. Assuming the uniform flow, we use the third equation where S0 is the initial bed slope of the system. From there, we can generalize the equation into a parameter SY, given in the fourth equation on the screen. The graph presented on the screen shows that the water depth increases linearly with X along the channel. When comparing the experimental and theoretical S1 profiles, the experimental data closely follows the theoretical data. The position along the channel increases linearly while the depth increases. For this graph shown on the screen, for the S2 profile, when comparing the experimental and theoretical data, the curve is not linear, like it was in the S1 profile. The relationship between depth and position along the channel is opposite of that with the S1 profile. For the S2 profile, the depth decreases as the position along the channel increases. And finally, the last graph, which is shown on the screen, is a comparison of the experimental and theoretical S1 profiles. The shape point on the graph is the experimental data, and the line represents the theoretical data. The experimental data has a linear trend and seems to line up closely with the theoretical values. The depth increases as the X position along the channel increases. Thanks for listening to the podcast today. Hopefully you guys learned a lot.